Hello guys, let's look at two ways how we can differentiate exponential functions. That is the case when we have a variable or a function to the power of a function and we're derivating with respect to that parameter of that function. So in this case, a function of x to the power of function of x, and we're going to be differentiating that with respect to x. So let's look at the first method, y substitution. So this is the slower method, but it is a bit easier to understand and you have less chances of making mistakes. We let y is equals to this part over here and then we continue forward. Now this is a bit lengthy process, so let's start with this. So we let y is equals to fx to the power of gx. Now of course I'm going to be doing an example later and we'll be going to do the same two methods later in this video. So right here, it would be kind of better if we had this function somehow on the numerator over here so that we can simply do product rule, and well, thankfully we can do that. We can just log both sides such that we get this, and from the log property this gx or the power will come down and in front of the log, so it will be like this. Now we can differentiate both sides with respect to x, so we get d ln y by dx is equals to d dx gx into log natural of the function. So we have to use the chain rule right here because we're differentiating a function of y with respect to x, but we really want to differentiate this with respect to y. So using the chain rule we can differentiate this with respect to y and then multiply it with dy, and we have the remaining dx over here. So what we're trying to find is this dy by dx over here. This will be equals to, here simply follow the product rule. This is gx into the derivative of this function, which will be 1 by this function into its derivative using the chain rule, and ln of fx into the derivative of gx. And now dy by dx, so the derivative of log natural is just 1 by y, and here this part will stay the same. So this will be gx f derivative of x by fx plus log natural of fx into the derivative of gx. And here this 1 by y, well, we can multiply both sides with y and this y will go over here. And finally what we can do is see that we originally let y is equals to this part over here and simply put that down. So this becomes f of x to the power of g of x times all of this, and no plus c because this is a derivative. This can be quite long and quite complex, but let's see the Euler log natural property. For this property you will have to know that, let's say you have a number a, variable a, constant, doesn't matter. This a is equals to e to the power log natural of a, because e to the power x and the log natural function are inverse of each other, and when they're together they cancel each other out, giving us the variable back. So that means we have f of x to the power of g of x. And you will also know, or you also know that the derivative of e to the power x is simply e to the power x, and we kind of want e to the power something over here. So let's look at fx for now because gx is already in the power. So f of x, let a is equals to f of x, simply replace that and you can see f of x is just e to the power ln f of x. So this is e to the power ln f of x gx, and now we're going to have to differentiate this. So When you differentiate e to the power something, you always get e to the power something back like this, and then you're going to have to differentiate the power over here, which is just following the chain rule. So you're going to have to differentiate this, and let's just do it directly. So first you'll have g of x into the derivative of ln of a function of x, which is 1 by that function, into the derivative of that function, plus log natural of fx into the derivative of g of x. So I'm going to write it right here, kind of running out of space. And here, e to the power ln g to the power x. I think I kind of skipped a step over here, because when you do this, you'll have first e to the power f of x whole to the power of gx. But due to the indices rule, this will come down, or this will multiply with fx. And right here, we can just do the reverse of that. We can put this as e to the power ln of fx to the power of gx, and then that e and ln will cancel, and you'll simply get the original function back. And inside the bracket, similarly to this, we'll have g of x, or not similarly, the exact same like this, f derivative of x, f of x, plus log natural of x into derivative of x, like this. Now, this is just a general form. This is why it may look kind of crazy. But let's look at an example on how we can use these methods to find the derivative. Let's differentiate this by first using the y substitution method. So, let y is equals to sine x square. This is sine of x square, not sine square x. Don't confuse that. To the power of tan 3 root x. Log natural both sides, and I'm going to skip a step right here, and this tan will come down, and we're going to have the log natural of sine of x square. And now differentiate both sides, and this will be dy by dx into d ln y by dy. Again, I skipped a step right here. I multiplied by dy on numerator and denominator both sides, just a chain rule. And here on the right hand side, this will be first tan 3 root x. This will be 1 by sine x square into its derivative, which is cos x square. And using the chain rule, I again have to find the derivative of x square, which is 2x, plus ln of sine x square into the derivative of tan of 3 root x, which is first 6 square root 3x into 3 into, well, the derivative of root x. Well, square root of x is just x to the power half, and when you differentiate this, this becomes 1 by 2 x to the power minus 1 by 2, which is simply 1 by 2 root x. We'll have dy by dx over here, which we're trying to find. This will be equals to, well, first the differentiating log will get 1 by y, and just move that to the right hand side. It will be y multiplying all of this, which is tan 3 root x into cos x square by sin x square. This is just cos theta by sin theta, which is cot x square into 2x, like this, plus the log natural of sin x square, 6 square 3 root x into 3 by 2 root x. So, like so. And I'm going to clean this up a bit, make it look nicer. And this y, well, we have to just replace that. There we go. We found our dy by dx. And let's move on to the second method. Simply, I'm just going to write it as e ln. So here, sine x square. This is just e to the power log natural of sine x square. And this will whole be raised to the power of tan 3 root x. But due to the integers law, this power will just multiply down like this, and we're going to have to find the d by dx of this. So first, this will always be e to the power whatever into the derivative of this power over here. And the derivative of this is, well, like we did before, like so. And finally, e to the power this, you can just raise this part to the power of that, e and ln will cancel, and just give that back. So in the end, we will simply have this over here, and I had forgotten 2x in this part, but I added it, don't worry, and there we go. So I prefer this ELN method because look at it, just 3 steps, and it's the same thing. It's almost like y substitution, but it's easier and the same process in mind, and you just have to differentiate ln sin x square tan 3 root x in this method as well as in the first method. So that's why I prefer this doing than the y substitution and all of that. But you're of course free to choose whichever method you feel easy with, but I prefer this, and maybe try this if you haven't. And if you learned something new, please like and subscribe. Thank you.